Also really quickly, I am Tanushka. This is my first time presenting. I'm very nervous, and although I do have some familiarity with ANOVA and I've done it before, what I'm going to be presenting today is primarily the statistical concept behind an ANOVA. What is it? Why we need to do it in the first place, and then a little bit on how it works. I'm not going to go very deep into the manual calculation because although we're taught it, I think in some undergraduate courses, at least in the one that I was in. But I feel that with the kind of data that we have available and the largeness, the majority of the data, it's really not feasible to do manual calculations, and we end up using softwares or R or something like that. And I think that there's going to be an R demonstration on how to do this also. So I'll just focus on the concept. And I do have the formula, but again, it's not going to go very, very deep into all of the aspects of it. Yes. I am also still a student, and while I'm familiar with this topic a little bit, I will probably make mistakes. So please don't hesitate to jump in or ask questions or correct me wherever I'm going wrong. Yeah. Okay, so let's start. Okay, yes. So this is just a really quick table of contents. Yeah. So the ANOVA, and the full form is, it's called the analysis of variance. Some clues as to like what it does in those three words. But basically, this is a statistical technique that was developed by Ronald Fisher, and that's also the reason why it's called Fisher's ANOVA. It's a parametric statistical test used to compare means between three or more independent groups. Now, I'm going to unpack this definition here. First of all, analysis of variance gives us an idea about what exactly an ANOVA does. If you all are familiar with measures of variability, so we have measures of central tendency, the mean, median, and mode, and then we have the measures of variability, which are the range or interquartile range, standard deviation, and variance. Is everybody a little bit familiar with that? Yes? Okay. So as I mentioned, so the ANOVA primarily uses variance and compares variances in groups to sort of, that's how it basically works. I'll go a little deep into that later. It's a parametric test. By parametric, I mean that it's used when your population is normally distributed and all of your groups are normally distributed. And also if you've done random sampling. So there are certain conditions you have to meet in your research to choose a parametric test. And if you don't meet those conditions, you do something called a non-parametric test. And you have, so for the ANOVA, depending upon the kind of ANOVA we use for research, there are non-parametric options such as the Kruskal-Wallis test and stuff like that. Yes, it's used to compare means between three or more independent groups. We'll focus on the number three or more. Why not below three? Because comparing means or looking at differences in means and groups is something that the t-test also does. And so in our stats lab, we've had a presentation on the t-test. And I'm hoping you all are also familiar with that a little bit. Yes? Okay. If anybody is not familiar, please don't hesitate to interrupt me or ask. Yeah. So basically, we needed a test to look at the differences between means in different groups when there were more than two groups. Therefore, we use the ANOVA. One-way ANOVA specifically is used to compare three or more independent groups on a single categorical independent variable. So there are different kinds of ANOVA. We have different kinds of t-tests also. We have independent t-tests. And similarly, there are different kinds of ANOVA. The kind of ANOVA I'm going to be presenting on today is called the one-way ANOVA. And that is basically very similar to an independent samples t-test in its concept. It's just that it's used to compare three or more independent groups. So as in the independent samples t-test, we want our two groups to be independent of each other. So for example, a repeated measures design and the data coming from that should not be used. Here as well, in the one-way ANOVA, we want our three groups to be independent of each other. And that's also one of the assumptions of doing an ANOVA. We'll get to that later. And so in an ANOVA, what really happens is that you're looking at the levels of each of these groups. Actually, just a second, let me just change the slide. Okay, yes. Yeah, okay. So in an ANOVA, you have three groups, and those three groups in the terminology as can be seen on the slide are basically called the levels of a factor. And that factor is the sort of grouping principle or the variable according to which the groups are made in the first place. So for example, like the example given here, your factor is age, and the levels of the factor or the groups that you end up with are, for example, 6-year-old, 8-year-old, and 10-year-old children's impulsiveness levels. This is the data basically that you get. Another example could be if you want to look at educational qualifications and you want to compare educational qualifications according to socioeconomic status. And so you take you make three groups of socioeconomic status: people with the data of their educational qualifications having a high socioeconomic status, their educational qualifications having a low socioeconomic status, and people, the data of their educational qualifications of people who have like a middle socioeconomic status. And then you compare the two. So am I making sense? Is everybody with me so far? Yes. Okay, great. So that's just some of the words that you're going to see probably. These can also be sometimes called more commonly like the independent or the dependent variable, and the factor is the independent variable, and you have levels of the independent variable itself, and then you have some dependent variable. Now, it's also very important to understand that because we're looking at levels of the factor cannot really be on a continuous measurement. So is everybody familiar with like the four measurement, nominal, ordinal, the scales of measurement? Nominal, ordinal, interval, ratio? Yes? No? Okay, I see 2-3 hands. Okay, great. Anukriti, you've been quiet. I hope you're understanding.
Yeah, I'm understanding.
Yes, okay, great. Yeah. Yes. Okay, so like in the scales of measurement, so nominal and ordinal are the ones that really fall, or nominal really is the one that falls into like a categorical sort of this thing, and then interval and ratio fall into like a more continuous, they're described as the continuous sort of scales of measurement. So in an ANOVA, your independent variable will always be categorical. And in a one-way ANOVA, you usually only have one of these categorical variables. So for example, in this example given on the slide, your independent variable is going to be age, and then you're going to have levels of that. Now, because you need to have levels, it's not possible to have that variable on a continuous, you can't just have data from 100 different people and like of their age. What you really want is like groups of data, and therefore you need levels, therefore it has to be on a categorical level. So it's not like you can sort of do an ANOVA with two continuous, like data of two continuous variables. That's not going to be possible. Your dependent variable, although, can be continuous. And so for example, impulsiveness levels could be measured according to like maybe a standardized questionnaire or something like that. And then data according to that could have been sort of put into these three groups of impulsiveness levels of 6-year-olds, 8-year-olds, and 10-year-old children. Okay. One very important thing about, actually let's go to the assumptions first. So with any statistical test, there are going to be some assumptions before we do that. Now these assumptions it's not like they're sort of really hard and fast rules, and we cannot in any case violate them even a little. So usually like real world data is pretty messy, and you don't really, it's possible that sometimes you're not able to meet these assumptions. And there are certain techniques or certain things that you will sort of, amend in your data to sort of account for these assumptions, even if they are violated. But talking on a very theoretical level, it's ideal that all of your assumptions are met, and only then you do, and then you could proceed with your one-way ANOVA. So your assumptions, and this is just for the one-way ANOVA, are that your DV or your dependent variable will be normally distributed. By normally distributed, this just means that the data falls into what is called a normal probability curve. Again, hoping everybody is familiar with that. Okay, great. You can use tests like the Shapiro-Wilk, or there's another one, Kolmogorov-Smirnov, I think. And these are options available on, softwares like SPSS, and which sort of help to, and they're basically tests to check normality. You also want to check for homogeneity of variances in groups. What this means basically is that, let's go back to like the full form of the ANOVA, analysis of variance. Homogeneity of variance essentially means that all of your groups have a more or less similar level of variance. There's not very high variability in one group and very low in the other, because again, that's going to sort of bias the results. Again, there are tests for this. You can use the Levine's test, which is also sometimes available. And lastly, you want to make sure independence of observations. You really want to make sure that there's no confounding variable in your data or between your two groups, and you want to make sure that both of your, all three of your groups, 3 or more, are independent of each other. So you can see how this is, again, very, very theoretically ideal, yes, but in real life, perhaps not as possible or realistic as we want it to be. One very important thing that I want to mention here is that the ANOVA is what is called an omnibus test. Ignore statistic here. I think I just forgot to sort of put that to delete that. But it's what is called an omnibus test, which basically means that it'll tell you whether or not there is a difference between three or more groups, but it won't be able to tell you where the difference is. So, for example, let's say that we want to test the effectiveness of a medication to reduce anxiety symptoms. And so we have, let's say, 30 people, and we randomly divide them into 3 groups of 10 each. And we give them, just a second, I'll just go to the slide for that. Where is it? Okay, I can't find it. Okay, hopefully everybody will keep up with me. Okay, so we have 3 groups. We're gonna randomly divide them so that each group has 10 people, and we give these 3 groups different amounts of the medication. One group gets no medication at all. One group gets maybe 10 milligrams of the medication, and the other group gets 20 milligrams of the medication. And what we want to test here, we want to compare these groups on the basis of their symptoms of anxiety, let's say using some sort of standardized questionnaire or rating scale or a clinical scale. And sorry, just a second. So we'll compare this and we'll do the ANOVA and everything will get our results, yes. And so even if we do get a difference, we do sort of reject our null hypothesis, whatever, we won't be able to point out just using the ANOVA where that difference is. For example, was it group 1 that differed from group 2? Was it group 2 that differed from group 3? Was it group 1 that differed from group 3? And that's really important because that's kind of the second step in knowing your research better and knowing your data better. Of course, you want to be able to figure out whether there is a difference or not in the first place to eventually find out whether the medication was effective or not. But then you wouldn't be able to figure out whether different levels of the medication also mattered, in the sense that whether 10 milligrams of the medication versus 20 milligrams of the medication made any sort of difference. And that is probably something you'd want to know if you were developing such a medication. So this is where post hoc tests come in, and you do these sort of tests. Some common ones are Tukey's, HSD, or Bonferroni corrections, and they have their own procedures. But what's really, so in softwares like SPSS, I'm going to keep sort of, most of my examples will be based on SPSS because that's where some of my experience comes from. And I've only sort of used that as a software. So yeah. So in softwares like SPSS, you usually have options to do post hoc tests alongside doing an ANOVA, and it'll just give you your results, and then you can look at whether there's a difference or not from the initial ANOVA, and then from the post hoc, figure out where that difference is, and then proceed with your research accordingly. Yes, is everybody with me so far? Okay. Yes. Okay, now I'm going to go into the theory behind an ANOVA. Now, okay, for this, we basically will talk a little bit about what essentially is variance. And we know that it's a measure of variability. We know that we perhaps might even know like the compute, like how to calculate variance and the relationship between a variance and standard deviation and stuff like that. But essentially, very, very basically, variance is variability from the mean. And it is one way of describing a distribution and describing the variability of the distribution. On its own, it's not used that much because standard deviation is a measure that's used a lot more often than the variance, because it seems to, it provides a lot more realistic, the variance is a squared measure. Standard deviation is the square root of variance, literally. So it provides a more realistic outcome that we can then compare to our data and make inferences. But in an ANOVA, variance is what we want to use. And how the ANOVA works is basically by comparing the variances between groups as well as within groups. Now, as you can see here on the slide, I've basically put these variances into 3 types of sorts. We're going to start with total because that's kind of the easiest. So the total variance is just a summation of the between samples variance or between groups variance plus the within groups variance. It's not really used for the conceptual understanding of the ANOVA, but it's used for the calculation. When you're doing the manual calculation of an ANOVA, you use the total variance, and sometimes you calculate like either the between or the within, and then because the total is basically between plus within, you can then figure out the other one that you've not calculated by just subtracting it. But for the conceptual understanding, 2 variances are the most important: the between samples variance and the within samples variance. As the name suggests, between samples variance basically measure how much difference exists between the treatment conditions. By treatment conditions, I mean your 3 groups, 3 or more groups. So let's go back to our medication example. Um, just for the people, I think a couple of more people have joined, and I'm not sure if you heard the example. I'm just going to repeat it really, really quickly again. We have 3 different groups, 10 people in each group, and what we want to do is compare the effectiveness of a medication for anxiety symptoms. Let's say we give the first group 0 milligrams of the medication, no medication at all. Second group 10 milligrams of the medication, 20, and third group 20 milligrams of the medication. We give them an anxiety questionnaire or some sort of clinical scale, and we look at their levels of anxiety symptoms while they are on the medication, and then afterwards we compare them using a one-way ANOVA. And what we're wanting to see here is how much the medication affected anxiety symptoms, or if it was effective for these symptoms in the first place. Now, between samples is really important in this situation, because if you can't measure, you need some sort of a calculation to measure how much difference exists between these conditions. Otherwise, how are you going to differentiate between the group that was given 0 milligrams of the medication and the group that was given 10 milligrams? Within samples, on the other hand, measures how much difference exists within the group itself. So as per sampling, we would have done a random sampling. We would have followed all sorts of rules of sampling and perhaps even matching people like they do in, let's say, clinical trials or something. Everything to ensure that our one group remains as homogeneous as possible. But still, there is going to be some random, naturally occurring variation just because of the fact that we're all human beings and we're all different from each other. And that kind of variation is what the within samples variation measures. So this is basically, you can think of it as the error in any, like the naturally occurring, completely random error that occurs. Now, the theory behind the ANOVA is essentially in its ratio. So basically, it's quite simple and complex at the same time. It's fantastic. So the ANOVA, how it works, it gives you this outcome, which is called the F statistic. And like we have the T statistic in t-test, we have the F statistic in ANOVA, and that it has its own distribution, like there's an F distribution. And the F statistic is essentially a ratio of the variances between and within groups. So we've talked about the different kinds of variances. F, as you can see in the slide here, is equal to the variance between treatments. So the variance between the group that was given 0 milligrams, 10 milligrams, and 20 milligrams, divided by our error term, divided by the variance within treatments. So if you look at this, the one that's down below, the calculation of F, it essentially says F is equal to systematic treatment effects, the ones that we actually want, because this is what we're doing the research for in the first place, plus the random unsystematic differences that will occur even in the between samples variance, because in any calculation there is possibility of like some error or some sort of differences, something happening, divided by our error term, which is the variance within treatments. So essentially we're cancelling out all of the random unsystematic differences and just being left with the systematic treatment effects, which is what we want. So is everybody with me so far, or should I repeat? This is kind of the core of what a one-way ANOVA is. And yeah, a couple of people, I'm just going to call out names because I don't see some people. I think I might have missed them. Devanshi, Irisha, and I think, I can't see your full name. Yes, Muhammad H. Wazirian. Are you understanding so far? Do you want me to repeat anything? No? Okay, great. Okay. When you say this part, do you mean this slide, the previous slide, or really specifically something? This slide, okay. So here what I'm trying to sort of explain is, so did you understand the different kinds of variances in this slide? Yes? Okay. Now what I'm trying to explain is how these variances make up the core of the calculation of the ANOVA. So when you do the ANOVA, any sort of ANOVA, not just the one-way ANOVA, even if you do a two-way or a repeated measures ANOVA, you'll eventually get something called the F statistic. Now, as in t-test, you have the T statistic and you get your T value, and then you compare that to your alpha level and figure out if your if your result is significant or not. Here as well, you get the F value. So you literally get like a table or something saying F is equal to this, let's say 0.254, for example. And then you'll compare that eventually with your alpha level that you've set according to your hypotheses and review of literature, and figure out whether your result is significant or not. What I'm trying to explain here is the ratio of how the variances and the different types of variance that I've explained in the previous slide connect to this F value. Because this F value is essentially the ratio of variance between groups to variance within groups. And so far, so good, Devanshi? Yes? Okay. So variance between treatments is the core stuff that we're looking for, right? We want to see if there are any differences in the different conditions. Let's say the group, so going back to my example on the anxiety medication effectiveness, let's say, so we want to look at the differences between the group that was given 0 milligrams of the medication, 10 milligrams, and 20 milligrams. And we hope, or we hypothesize, that there will be some sort of difference. And we want that because that is when the medication would, that is how we show that the medication does have an effect on reducing or increasing or some sort of effect on the anxiety symptoms. So we want the variance between treatments. Now, the variance between treatments will give us the systematic treatment effects, yes. It'll tell us if there is any differences. Like, for example, perhaps the group with 0 milligrams, unfortunately, their anxiety symptoms get worse because of no medication after a month. Whereas the group with 20 milligrams, their anxiety symptoms improve after just 1 week on the medication. And the group with 10 milligrams of medication is just constant. Their behavior is constant. Their symptoms are constant. There's no difference. We want to compare all of these. So your variance between treatments is really, really important. And that will include some of these systematic treatment effects. And then simply because this is a calculation and also a calculation of human behavior, and there is bound to be some sort of random chance error, there's bound to be some sort of unsystematic differences. So your variance between treatments also includes that. What I'm saying here is that variance between groups, the numerator of this F formula, includes your systematic effects, plus a very minor error term, let's say. Your variance within treatments, that's the denominator of your F calculation here, is essentially just your random unsystematic differences. Because your within variance is not really, is just variance arising from the fact that in your group you have 10 different human beings and you're trying to portray their behavior as a group. So there will be some sort of variation because it's not one person that you're comparing. It's 10 different people. Yeah, are you with me so far, Devanshi? Yes? Okay. So your F statistic is nothing but a ratio of these two. So you're just comparing between samples variance to within samples variance. And what you're essentially doing is, the reason you're sort of comparing your systematic treatment effects to the random unsystematic differences is because we want to make sure that the treatment effects is something beyond or larger than the unsystematic differences. You don't want treatment effects that are in or are mathematically smaller or equal to unsystematic differences, because then how can you for sure say that they were caused because of the effectiveness of the medication and not just because of some random error? And so you want to be really, really sure of that. And this sort of like, so what I've put here is basically a way, this little thing I've put here in the bottom is basically just to sort of explain how the F statistic is helping us do that. Did that make sense? Yes? Okay. Let me know if you have any more questions. Okay. Yes. Now, so if the variation between the samples or between the treatments is larger than the variation within the treatments, then the groups are different. And we want this. We want that the variance between groups is larger. Because as I said right now, this is what helps us to be very sure of the fact that there is some sort of difference in these groups that is caused by something apart from random, unsystematic, or chance error. Okay, now I will, yes. So this is just a very quick, I'm just going to quickly explain the differences between an ANOVA and t-tests. Most of this is just something I've talked about before. But yes, there are two different kinds of statistics used. Like the t-test uses the t-statistic, a t-distribution. ANOVA uses the f-statistic. There is a relationship between the f-statistic and the t-statistic, but I'm not going to go into that today because I'm also a little confused by how that works. I don't want to confuse all of you. Yeah, so now one thing that is also really important is that this f-statistic or the t-statistic in a t-test is not our final, it's not the end all be all and it's not that we can just get our S statistic in an ANOVA and say that our ANOVA is done. That's not how it works. We need to actually test our hypothesis, and we need to set our alpha level and test our F statistic against our p-value, or against our alpha level, sorry, not the p-value. By alpha level, I mean, so for example, the most commonly used that I've come across so far is 0.05, but you can also use like a sort of stricter 0.01 alpha level. Is everybody familiar with the concept of p-values, alpha levels, hypothesis testing? Yes? Yes, okay, great. So your F statistic, again, not the end all be all. You have to associate it with the alpha level, test it against the alpha level, come up with the p-value, see if that p-value is significant or not significant according to your alpha level, and then make your decision. I have also, in my hurry to make the PPT, switched the second. I don't know if some of you caught that, but yes, go ahead. Federico, I hope I pronounced your name right.
Yeah, you pronounced it right. I don't know if I'm correct or not, but I think the column with the t-test, the one that says 3 or more levels, I think it's the other way around.
Oh,
I'm
yes.
not sure.
Yes, that's a mistake.
Right.
I'm just gonna, what have I done? Just a second. Yeah, this is also a mistake. Can you see what I've highlighted right now? No? Okay, just give me a second to change these. This is 2, not more. And this is 3 or more. Yeah. Yes, I had mixed these two things up. Thank you so much for pointing it out. Okay, restart. ANOVA, S statistic, t-test, t statistic, it doesn't end here though. We need to associate that with the p-value, test our hypothesis, and only then can we make a decision accordingly. As mentioned before, an ANOVA is used when you have one categorical IV, that's independent variable, with 3 or more levels. It could be age, it could be socioeconomic status, it could be some sort of like levels of the medication that you've given that you want to test the effectiveness of. For a t-test, you want one IV with 2 levels, not more than that. The number of DVs remains the same, especially in a one-way ANOVA. I'll make one other change here, and the one-way ANOVA. There are different kinds of ANOVAs. There is also a kind of ANOVA called the two-way ANOVA, where you can actually have 2 independent variables, still categorical, and then do a sort of factorial design. But we're not going to get into that today, thankfully. Yeah, any questions on the slide? Should I move on? Okay, moving on. Okay, very interesting. Does anybody want to answer this question? Why do we not run multiple t-tests instead of just doing an ANOVA? If the only difference between an ANOVA and a t-test is that an ANOVA is used for 3 groups or more, and t-tests are for 2 groups, why can't we just do 2 or more t-tests? Or yeah, why not? There's a clue also. Anybody wants to answer? I don't understand this emoji, Pooja. What is this?
No, it's a very good question which I had not asked before, so that's why that emoji.
Okay. So the thing is, so whenever we run any sort of statistical test, we have possibilities of type 1 error happening, type 1 as well as type 2 error. Is everybody familiar with the concept of these 2 errors, type 1 and type 2? Okay, Devanshi, no, I'm assuming. No? Okay, great. Gives me more to explain. Okay, so a type 1, so these are 2 really common statistical errors that can happen when we do any sort of test. So a type 1 error is what is called a false positive, which basically means that, let's go back to our medication example. It's going to be, you all are going to be very tired of that example by the end of this. But let's say that we do all of our research, we collect all of our data, we do our analysis, divide our groups, everything. We get a result and we see that there is a significant difference. And we're really happy because that's what we wanted. It proves our hypothesis. We rejected the null hypothesis. That's fancy statistical language for basically saying that we have a significant difference between our groups, which means that the medication worked, all is good. But it's possible that we made something called a type 1 error, which means that what we've gotten right now, the result that we've gotten right now is a false positive. Actually, what the result that we're getting is because of an error. It's showing us a positive, a significant difference, when in actuality, there is no difference to be found between these groups. Now, this happens when sometimes your alpha level is not as stringent as it should be. For example, if you've taken an alpha level of 0.10, for example, so the most commonly used is 0.05, which means that if you convert that into like percentage, which means that you have 95%, like with 95% surety, you can say that your results are not due to chance, but you still have margin for 5% error. With a 0.10 alpha level, that margin would be increased to 10%. So it's only, so what this basically means is when I say that, let's say I have a significant difference between my groups, I'm saying that, and this difference is calculated on an alpha level of 0.10. And what I'm saying basically is that, give me a second. What I'm saying is that I can say this with 90% surety, but 10% I'm not sure. The more margin you have for that error, from 5% to 10%, 1%, 2%, whatever, the more chances you have of making a type 1 error, which will lead you to a false positive. We definitely do not want a false positive, because imagine you're in a situation where you're developing this drug and you get a significant result and you give the go ahead for developing and for sort of final production and everything, and it goes out to a lot of people and causes them damage. You do not want that. So one way to sort of reduce type 1 error is actually to make your alpha level really, really stringent. And that's why you use like really, really small alpha levels like 0.01 or 0.001 also sometimes. Type 2 error is sort of the opposite in a way, I think, where you have a false negative. So you think that there is no difference between your groups. You've accepted your null hypothesis. There's no significant difference between your groups, but in actuality there was. So in this situation, that's also very, very harmful to you, because you would come up with a result of no significant difference, get dejected, probably stop production. But in actuality, there was a difference. Perhaps a small difference, perhaps a large difference. There was a difference. You just missed it, or because of error. And these two errors are not just possibilities with a one-way ANOVA. It's something that could happen with any statistical test. It could happen with t-tests. It could happen with, it's just the risk that we take when we're doing any sort of statistical test. There are some chances for error always. So coming back to the question, Devanshi, did this make sense? Yes? Okay. Coming back to the question, why would we not run multiple t-tests is because every time, so the t-test, think of the t-test as one statistical test, right? So when we have two groups, we can just do one test and sort of get our result. When we have three groups, we're going to have to do how many? We're going to have to do a lot of tests. We're going to have to do a test comparing group 1 to group 2, group 2 to group 3, as well as one comparing group 1 to group 3 to actually get our proper result. That's 3 t-tests. Every time we do a t-test, say that we keep our alpha level at 0.05, we have 5% chances for error. The first time we do a t-test, 5% chances for error. Second time we do a t-test, 5% chances for error. Third time we do a t-test, 5% more chances of error. This doesn't mean 15% chances of error, but in your entire experiment. And let's say that this wasn't the end of your statistical analysis. Let's say your data was really, really complex and you had to do more statistical tests as well, all of which come with their own levels of error and their chances for error. Eventually, your error is going to build up to such a point that you have a lot more chances for getting like type 1 error. You're increasing your chances for type 1 error. Therefore, we need one statistical test that can sort of do the function of multiple t-tests in a way. And we need one so that we can minimize our chances for statistical error as much as possible. Okay, all good so far? Any questions? No questions? Okay, great. Okay. Yeah, I actually think I am done. This was it. And yes.
Thank you so much, Tanushka. That was really amazing.